Welcome, welcome. Let's talk about Benzyne reactions. So there's an interesting counterpart to electrophilic aromatic substitution reactions. Um, in this case, you can make use of somewhat good leaving groups present on the benzene ring, such as the chloro group right here. It was shown many years ago that when you react a molecule like chlorobenzene with a strong base such as sodium amide, and you do this in liquid ammonia, specifically to preserve the basicity of the amide conjugate base, something interesting happens. You ultimately end up reacting in such a way that the benzene ring becomes electrophilic. So it is no longer acting as a nucleophile, but rather the opposite. The nucleophile in this case is the amide. And you see a substitution happening. Basically, the chloro is substituted for the amine group in this reaction. Now, the way this happens is a little bit counterintuitive to you, what you might be guessing right now. But one thing that I want to also show you is that you could also achieve the same event if you start with a dihalogen ortho in substitution. You can treat this with magnesium to basically create a Grignard reagent, at least initially, and then you can introduce your sodium amide molecule to get to your final endpoint. At the end of both reactions, you still have to quench them so that they end up with a neutral molecule. But as I was mentioning, the intermediate that leads to these products, it's not a straight reaction like an SN2 reaction or even an SN1 reaction for that matter. In fact, you end up forming something that you would think shouldn't even really be a possibility. But as a result of the strain that this molecule is going to possess, is that these reactions move forward. And specifically, the intermediate is what we call a benzyne molecule. Simply put, one of the centers of the benzene ring ends up with an additional double bond, creating technically an alkyne. In reality, this is more like carbanion next to carbocation, but either way, it is a very unhappy and reactive molecule. So this benzyne intermediate is not something you isolate. You just form it in situ, and you have your reagent that's going to finalize the substitution pretty much already present in solution as the benzyne molecule is forming, so it's ready to go. If you don't, the benzyne will end up doing a bunch of other things, and you'll end up with a mess in your reaction. All right, but this will allow you to react the ring with nucleophiles as opposed to electrophiles. So these reactions do bear the name of nucleophilic aromatic substitutions as a result of that. So let me show you how this works out. First, we're going to start with just the chloro substituent. Now, in the presence of the strong base, the sodium amide, and this being done in liquid ammonia, what you will end up doing is deprotonating the ortho position in respect to that chloro group. The CH bond, those sets of electrons will move over to the next adjacent carbon, the one where the leaving group is located, and then the leaving group will take off. And this is ultimately what will generate the benzyne molecule. So then what will happen is that a second equivalent of the amide nucleophile will then come by, attack one of the positions of the benzyne group, and you end up kicking away one of those two electrons from the pi system to form basically a carbanion, a sodium carbanion. And then it's at this point that you need your slightly acidic media to quench the reaction to reprotonate the carbanionic sites. So this ultimately gives you that substitution, and it's all via this benzyne reaction. Now, the second option that I mentioned involves the magnesium reagent. With magnesium, you can form a Grignard intermediate, but in reality, the way that this happens is that the magnesium attacks one of the two halogens, and the electrons of that halogen or that carbon halogen bond move over to the next adjacent carbon where the leaving group is located, kicking away the leaving group, creating your Benzyne reaction, and then you form a magnesium halide byproduct. And then when you introduce your sodium amide, the amide reacts with the Benzyne in the same manner as we saw up here, creating your carbon ion, and then upon quenching it, you end up producing your aniline. So it's an interesting way of doing this stuff as well, right? So you have now two ways of introducing the amine group if you need to on the benzene ring. Okay, so pretty much, like I showed in the previous example, right? You can treat this ortho-bromochloro derivatives with magnesium to create your Benzyne, but you could do extra things with them. You don't necessarily need to react them with amide. You could react them with other alkyls. So, for instance, you could be forming a regular Grignard reagent like the ones you've seen in the past, but in the process, you could also generate your Benzyne reagent. And since a Grignard reagent is still a good nucleophile, the moment you form your Benzyne reagent, the Grignard can attack your Benzyne that has been freshly formed. You form now technically a Grignard, and at that point you can quench this reaction. You could quench it with water or acidic water, or you could actually quench it with an electrophile such as diiodine to introduce now an iodo-substituent in that ortho position. So this actually gives you a lot of flexibility as to what you can place on the benzene ring altogether. And just to kind of give you a full scope of how this works out, well, the R group, which is basically the nucleophile that attacks, those could be alkyls, Grignard alkyls, Grignard vinyls, Grignard alleles, Grignard alkenyls, Grignard, phenols. It could just be your sodium amide, like we showed earlier. And then for your electrophiles, it could be literally just hydrogen that comes from water, or you could just react this via SN2 reactions with primary alkyls to introduce a second alkyl in this position. That could also be an allele. That's a good SN2 substrate that can be used to install in the ortho position. You could produce carboxylic acids at these positions, or even halogens. And, just to be sure that we're on the same page about it, you introduce the primary alkyls as long as you have a primary halo alkane as the substrate. You could introduce the allele substituent if you have your chloroallele molecule. You could introduce a carboxylic acid upon treating your technically Grignard with CO2, followed by acidification with acid. And your halogen simply just by reacting the Grignard you have from, with the dihalogen itself. So this is a pretty powerful reaction. So I'm just going to show you an example of how this works out, and with that we'll finalize the lecture. So let's say that we want to prepare the following molecule. So we have this biphenyl system with an iodo substituent, and the thing to realize here is that one, you have one of the phenyl groups ortho to the iodo. The second thing is that this phenyl group cannot be installed using a Friedel-Crafts alkylation because this is an sp2 center, not an sp3 center. So that's one of the restrictions. And because these are ortho to each other, this cannot tell you that, okay, this is not going to be your typical electrophilic aromatic substitution. Instead, we got to do this via the formation of Benzyne to make it happen. And that's mostly because of the fact that we have to put an extra benzene ring on an original benzene ring to begin with. All right, so we're going to use the Benzyne route to introduce the aryl and iodide groups to each other. And you just have to start with a dihalobenzene to do the process, right? So basically, if you want to generate this molecule, which I'm abbreviating the second phenyl ring as pH, well, the way you could do this is to basically introduce the other group by reacting the Grignard derivative with diiodine. And then this Grignard derivative can be made directly from the Benzyne intermediate if you react the Benzyne intermediate with phenyl Grignard. And of course, the benzyne intermediate itself can be formed directly from bromochloro, ortho-bromochlorobenzene. So those are kind of the things that you have to think about, right? Like, is it possible to do it via the electrophilic aromatic substitution route? If not, what about the nucleophilic aromatic route, which is basically the benzyne intermediate? So hopefully you have found this sort of videos helpful. But just to give you one last thing, because this is kind of important since we're talking about the bromo and chloro benzene derivatives. As far as how you make this thing, notice that they both have to be ortho, right? Because if they're not ortho to each other, then you're not going to be able to do the Benzyne reaction with magnesium, as I mentioned earlier. The prepositions have to be blocked. So we have to do this, one halogen at a time, right? And we're going to block the prepositions to make this work out. So one way that you could do this is to start by having, let's say, the bromo pair substitution blocked with sulfonic acid, right? And that happens before you chlorinate. So you will first sulfonate your bromobenzene. You then will undergo a chlorination to get the chloro ortho to the bromo substituent. And although the sulfonation is going to give you a mixture of ortho and para, you'll have a little bit more para than ortho. So you'll have to do a little bit of cleanup. However, the ortho byproduct that you separate can be turned back to bromobenzene simply by treating the ortho derivative with dilute sulfuric acid. So you don't necessarily have to lose it. If you do this a good number of times, you could eventually get to like 99% of just the para substitution. And then bromobenzene itself can be formed from benzene just by using dibromine and iron 3 bromide in the process. So this is just to give you an idea of how you make this molecule in the first place. In reality, you probably just buy it from a chemical supplier, but under the assumption that you don't have that option, or the supplier is got this molecule back order or whatever else, well, you have some means of making it yourself. All right, so with that, we finished this lecture. I hope this was instructive to you and gave you some ideas, synthetically speaking. And in the next set of videos, we're going to get into more mechanisms, this time around looking at the carbonyl compounds. So see you then. Bye-bye.